important. All right, so getting back to the slides, again, very important slide. Make sure you go and review this. This is the system we are studying. We want a mathematical model for it. And the mathematical model for this is this equation, this differential equation. So here's the differential equation that describes the behavior of the system. You will learn to solve these differential equations, and some of the simpler differential equations you just try functions by trial and error. So here's a solution to this differential equation. Okay, what does this solution give you? You see, it gives you the position of this object as a function of time. Once you know the position of this guy at all times, you know everything there is to know about the system. Okay, so once you have this x as a function of time, you can take the derivative and calculate its velocity as a function of time. Take the derivative of that and calculate the acceleration as a function of time. Okay, so you have the position, velocity, and acceleration of the object as a function of time, and that's what you wanted to know. Like I said, this is a second order differential equation, meaning there's a second order derivative. And because it's a second order differential equation, two constants that were not in the equation appear. And those are determined by the initial condition. A, like I said, is the amplitude of oscillation. So if you pull it 10 centimeters from the equilibrium position and let go, that would be 10 centimeters. If you pull this guy 15 centimeters from the equilibrium position and let it go, A would be 15 centimeters. And phi is related, let's say you pull it from 10 centimeters and just let it go, then without giving it any velocity, then phi would be 0. If you gave it a kick, then phi would be non-zero, okay, and so on. So A and phi are constants that are determined by initial conditions. So A is the amplitude of motion, omega is the angular frequency, phi is the initial phase, and A and phi are determined uniquely by the position and velocity of the particle at t equal to 0. So x at 0 and v at 0 will determine A and phi. Okay, so that's the general theme. And now you'll see 3-4 other examples that we'll see 3-4 other systems whose behavior is given exactly, described by exactly this equation. You'll see systems that look very different from this, but their behavior will be described exactly by this differential equation. Okay. All right, so you saw that the position of this mass as a function of time was given by this equation. This was a sinusoidal, a cosine or a sine function. Okay. And we can illustrate this, that this indeed is true. And this can be illustrated in a lab. So you can have a roll of paper that's scrolling at a constant velocity. You can attach a pen to this mass, get it to oscillate, and you'll draw out a sine or a cosine function. Okay. Here's a physical illustration of the fact that this is a solution of that. This is a solution. This solution correctly describes the position of that mass as a function of time. All right, so the period of oscillation, as you saw, the period was the time it took for the object to oscillate once. The period is given by 2 pi times square root of the mass divided by the spring constant. And again, this is this formula works assuming the spring mass is negligible. Anyway, so here's the period for an ideal spring, 2 pi times square root of mass over m. And this makes sense. So let's make sure that it makes sense. The greater the mass is attached to a spring, you think that it would take longer to oscillate. The stiffer the spring, the stronger the spring, the faster it would oscillate. And that's what that equation tells you. Greater the mass, greater the period, slower the oscillation. Stiffer the spring, greater K is, smaller T is. Okay. And by the way, frequency is how many times does it oscillate per second, per unit time, and frequency is inversely related to period, and it's given by that 1 over 2 pi times K, square root of K over M. All right, so this is a summary of what we've studied. Okay, so our system, the behavior of our system was described by this differential equation. The solution to this differential equation is that this gives you the position of the mass as a function of time. You take the derivative of that, that'll give you the velocity as a function of time. And you see sine or cosine functions, the maximum value they can have is 1. So the maximum velocity would be a omega, okay, plus or minus a omega. And that happens, you remember that the velocity is maximum at the equilibrium position. The acceleration is given by the second derivative of the position, which is minus omega squared a cosine omega t plus phi. And again, the maximum value of cosine is 1, so maximum acceleration is a omega squared, the magnitude of the maximum acceleration. When this is minus 1, it would be a omega squared. When this is plus 1, it would be minus a omega squared. So anyway, the maximum values for the velocities are a omega, and for the acceleration, a omega squared. All right, so now let's look at this simulation. Well, we already saw this, so let me pull it up. So let's get this started. Okay, again, so you saw that by solving the differential equation, we got the position of this guy as a function of time. And now what the simulation is showing you is, like I said, in an oscillator, energy is being converted from one form to another. So you see energy is going back and forth from kinetic to potential. But the sum of the two, which is the total energy, that is constant. Okay, so that's true in a frictionless system. So the sum of kinetic and potential energy will be constant. Okay, and that's what we'll see in this slide. Okay, so the kinetic energy is 1/2 mv squared, and you can substitute the expression for V from here and put it in there, and you get that expression. The potential energy is 1/2 kx squared, and you can substitute the expression from x from the previous slide and put it there. And if you add the two, the total mechanical energy is kinetic plus potential energy, you get a term, see, that's not dependent on time. Kinetic energy depends on time, potential energy depends on time, but their sum does not depend on time, and it's a constant. Okay, so the energy of a simple harmonic oscillator remains constant as long as there's no friction. You can express V in terms of the position. So you can calculate the velocity of this object when the mass is at x, okay? And it's the square root of plus or minus square root of this, okay? And the velocity is negative when it's moving to the left, and at every given position, it can be either moving to the left or right, and that's what the plus and minus signs are about. And you can see that when x is equal to a, so when the object is at its amplitude, at the extreme position, when x is equal to a, the velocity is 0. So at the end points, the velocity is 0. And so anyway, here's velocity as a function of time. All right, we will pause now. And again, I'll let you guys ask questions, because